Okay. Okay, there's just 1, 2, 3, 4, 5. I see Alex also connected. There's just a few people in. So for those who have already joined, thank you very much for joining. We will be waiting a few more minutes to let everyone in, and then we will be starting with our second webinar of the SUBBIMATT project. Okay, I think we can start if you agree. So thank you everyone for joining this second webinar of the SUBBIMATT webinar series. My name is Andrea Spotti. I work for Tinexta Innovation Hub, and we are in charge of the communication, dissemination, and exploitation of the SUBBIMATT project. Today, along with me, there are three colleagues from the Technical University of Athens. Dr. Kate Trompeta, who will be give a short introduction about the lab and NTR hydrogels. Then Faye Papadopoulou, who will talk about the synthesis of NTR hydrogels. Konstantinos Zafeiris, who will give a presentation about rheological measurements. And last, Kate will take again the floor with a presentation on wettability measurements. The webinar will last about 1 hour. And the questions and answers session will be at the end of the webinar session. So if you have questions, please write them in the chat, and my colleagues will be responding to all of your questions. The meeting will also be recorded, is being recorded, and as we did with the first webinar, we will be uploading it on SUBBIMATT project website, on SUBBIMATT project YouTube channel and LinkedIn, so you can find all the information. I will also be leaving some of the links here in the chat of the meeting. So I think I've said it all, and I would now leave the floor to Kate for the first introduction. Thank you.
Thank you very much, Andrea, for the nice introduction. As mentioned before, I am Kate Trompeta. I'm a chemical engineer working in the National Technical University of Athens, and especially in the research lab of advanced composite nanomaterials and nanotechnology. Today, me and my team will talk about negative thermoresponsive hydrogels and short NTR hydrogels that can be used in smart textile applications as they are described in SUBBIMATT project, which is a project regarding the sustainable bio-based, bio-inspired materials for smart technical textiles. So I would like to start with a few words about who we are. Our laboratory of advanced composite nanomaterials and nanotechnology has been established since 2006 and has extensive experience in the designing, production, characterization of advanced composite and nanomaterials. We have several units and teams in our lab, as you may see here, but the two main teams that are working in SUBBIMATT project is the chemical synthesis unit and also the chemical vapor deposition technologies unit. Today, our work represents some of our chemical synthesis, and you can see here that we have a wide portfolio of advanced materials and nanomaterials, different type of materials that we can synthesize. And the whole work in SUBBIMATT project started due to the fact that we could synthesize different subs. Subs stands from superabsorbent polymers. So we were able to tune this type of structures with different polymers and different functionalities. So that's why we thought that we could also proceed with the negative thermoresponsive hydrogels, which have a similar structure and similar way of synthesis as my colleague Faye will present you during her presentation. So we started with this idea to have a smart textile that can control humidity. And of course, we need specific characterization of the performance of these materials and also for the smart textiles. That's why we also exploit some of our capabilities in materials characterization and specifically the structure and surface analysis and several of our microscopies in order to be able to assess the performance of the materials. Today we will speak about the rheology measurements. Konstantinos will be the speaker for this specific testing, and also I will show you some of our wettability testing at the end of today's webinar. So why to use thermoresponsive hydrogel on textiles? Temperature is attractive as a trigger because it's simple, reversible, and directly relevant to wear and comfort. A hydrogel can translate the thermal stimulus into a change in water content and change conformation. That molecular change can be felt macroscopically as a change in wetting, permeability, or adhesion. So the textile stops being just passive and starts responding to its environment. So actually what we do is to exploit the temperature input, the differences in our body in respect also to the environment. So to take, for example, the heat from our body, which is an easy and reversible trigger. The hydrogel can respond, so it can swell or shrink, and also to have some surface energy shifts. With this, we have an effect on the textile, and this changes its wetting, its permeability, its adhesion, or the transport of air and humidity through its pores. The necessary testing is about the textile performance after its functionalization with any material, for example, here are the ATR hydrogels. So what we want to check is the contact angle versus the temperature and time, its water uptake or water spreading or wicking behavior, the air and water vapor permeability after its coating. And actually, this is the work of Centex Bell, SUBBIMATT coordinator that are checking the air and water permeability, the repeatability of switching of the actual fabric, and the performance under realistic humidity and bending. A useful smart textile is not only responsive, it must remain responsive after handling, moisture exposure, and repeated thermal cycles. That's why we need to fulfill the performance and the functionality, but of course, to withstand washing, abrasion, and to check the coating retention, also to have tensile and flexural response during handling, compatibility with other textile functions, also to ensure that the aging stability during storage and use can be fulfilled, and of course to fulfill the safety, comfort, and biocompatibility when this is relevant. I would like to close this introduction by introducing the lower critical solution temperature, which is the property that we are studying actually. What we need to quantify in the responsive phase itself. First of all, the swelling ratio or thickness as a function of temperature, the response time and reversibility over many heating cooling cycles, the thermal transition, chemistry, and morphology after cross-linking, and all these are connected, as you may see, with different parameters. For example, the swelling ratio is a function of temperature. Similarly, also it's affected by the thickness because it shows how much the hydrogel swells or collapses. The response kinetics are also really important because they show how fast the coating switched. Also, the morphology and chemistry of the fabric itself and also the coating shows how the network interact after processing. And we have also the cycling stability to show us if the response survived after repeated triggers. Where is the LCST or effective switching window, which is something that can be also identified by the rheological measurements that will be presented in the next. And also to answer the question on how much coating remains after swelling and drying, which is also a matter of stability. So you need to remember what is the LCST. So it stands for the lower critical solution temperature. Below LCST, the network is hydrated and swollen. Above of it, we have a less hydrated polymeric network that can be also collapsed. So it means that the water is expelled and the polymer chains collapse. These are done through the increase of temperature. So now I will give the floor to my colleague Faye, that she will present us how she has synthesized the NTR hydrogels and how she was able also to identify the CST. So thank you from my side.
Hi, everyone. I'm Faye, a material scientist from University of Crete, now working and doing my PhD in the Nano Lab. Very excited for that and working in the SUBBIMATT team. Can you see my screen? Okay. So I'm gonna talk about mainly the synthesis of those NTR hydrogels. As Kate mentioned, the LCST acronym stands for lower critical solution temperature. And below this temperature, the hydrogel is hydrated, swollen, and soluble. And above that temperature, the hydrogel becomes hydrophobic, collapses, or turns into a harder gel. And this transition is mainly driven in the water and polymer interactions with the temperature. And the purpose for this, or the applications that can be utilized in, is stimuli responsive systems, control release or activation of functional agents, smart coatings like the one we're seeing today. So smart coatings and finishes, selective removal processes, and in general, energy, textile, and biomedical applications. So in order to synthesize the NTR bio-based hydrogels, we first need to think how are we gonna design those experiments. So we started with bio-inspired design approach and selecting raw materials, selecting the proper raw materials, and formulating the pathway in which we're gonna synthesize and then assess those hydrogels. Evaluation was a very important step in that. Evaluation of the LCST, the solvent systems, the temperature, the processing conditions, in order to validate the material performance and then consider the scale up. So we started testing, and we did a lot of testing, and we continue testing, as you see, until we find a synthesis that we liked. The synthesis was composed of NIPAM, or isopropyl-acrylamide, which is a thermosensitive polymer that changes behavior with the temperature. It has a very narrow temperature range. It's about 28 to 34 degrees. And using HPMC, or hydroxypropylmethylcellulose, which is a common polysaccharide found in our cells, and also it's a good viscosity modifier that improves structure and processability. Together, they form a hybrid hydrogel with tunable properties. This was to create a processable hydrogel that is suitable for the textiles applications we work in SUBBIMATT. The key concept here is that the NIPAM gives the temperature sensitivity and HPMC gives the mechanical strength and the viscosity control that is needed for this gel. Free radical polymerization forms the final network, and for this reason, we have APS as the initiator and TEMET as the accelerator. The initiator and the accelerator are vital because elevating the temperature above the NIPAM and HPMC transition temperature results in a collapsed polymer network that can't be further processed. So keeping the temperature low, room temperature ideally, or even lower, forms NIPAM polymer, and mixing it with HPMC hydrogel, we can actually make this hydrogel that looks like this. So it's a clear gel that when it hits above 32 degrees, you see it gets white. The white part actually represents the kinetic of the polymeric chains and the collapse of the NIPAM structure along with the HPMC. The HPMC here and the NIPAM, they shrink, they release water, so the hydrogel becomes more dense and a harder gel. This is why it stays at the bottom, towards the top upside down bottle, and while on the bottom row of pictures, while it cools down again, below 32 degrees, it becomes transparent and glides down like a liquid. So here we have a little droplet under a stereoscope in order to assess this transitioning in this gel formation. We have here a little time lapse, let's say, that is of the hydrogel during heating. At room temperature, the gel is fully swollen, and as temperature reaches 33 degrees, the hydrogel gradually contracts and becomes more pronounced after 1 minute and even more after 5 minutes. This demonstrates the thermoresponsive behavior that our chosen hydrogel exhibits. And okay, we did it. We tested it. We did multiple variations of that. But what about the procedure? Is it robust? Is it reliable? Can NIPAM and HPMC be mixed thoroughly to replicate this result over and over again? So we did ATR spectra in different batches of our experiment. And these ATR spectra, as you see here, are from 3 different samples, and from the one sample we did in 3 different areas. In order to do that, we freeze-dried the hydrogel from 3 different batches in order to see the replicability for our process. The peak positions and the relative intensities are similar, as you can observe, and this indicates the reproducibility of the chemical structure between the independently prepared samples. So with this, we can confirm that our synthesis procedure is robust and reliable. And now comes a bit of a difficult issue. How can we graft and secure this hydrogel that we made onto the fabrics? The first route we chose was just to disperse with a cross-linker and see how the fabric reacts. That was not enough. So we tweaked, let's say, our synthesis route here, our coating route, let's say, and we immersed our fabrics in the cross-linker, which is MBA. We used the relative amount of gel that each fabric absorbs. We did testing on that, and we found out how much the fabric absorbs, and then we used 5% of this onto the fabric directly. Then we layered the hydrogel on top and let it dry completely. This resulted in fabrics that are coated and fastened onto the fabric instead of just on itself. And since we are trying to work with hydrogel that does change temperature, does the temperature indeed change onto the fabric? So we tried and tested that. These pictures are from a stereoscope, again, using a hot plate underneath. And here especially, we took a picture that was on the wet fabric, coated and with a cross-linked hydrogel on top of it. And we actually observed that changing the temperature from 19 degrees to 36 degrees does change the pore area that can be observed. So we did a hydrogel that is composed, that has 50% bio-based content using the HPMC, the polysaccharide we are using. It is temperature responsive, and we use it to create smart textiles. We tuned its mechanical properties to process it easier with different types of either injection or just butter coated, and we have this result. Of course, our work is in progress, but thank you so much for listening to me, and Konstantinos, you can take the lead.
Thank you very much, Faye, for the presentation and the introduction. So let me share my screen, and hopefully you can see the shared screen now. So good afternoon, everyone. My name is Konstantinos Zafiris, and I will present the rheological characterization of the NTR hydrogels developed within the SUBBIMATT project. So I will start with the role of these hydrogels in smart textiles and their working principle, and I will afterwards introduce the rheological methodology that we used in their characterization. And next, I will present the experimental results, starting from fully bio-based systems and the transition to hybrid formulations. Finally, I will discuss the interpretation of the results and some takeaway messages. So in SUBBIMATT, NTR hydrogels are a key enabling material for smart bio-inspired textiles. They allow dynamic control of the textile porosity, enabling adaptive breathability and thermal comfort. Now, this concept is not new. It's inspired by plant stomata, which regulate gas exchange through opening and closing mechanisms. Now, their function, the hydrogel function, is based on the lower critical solution temperature, as we referred before. So below this temperature, the hydrogel is swollen and, when in a fabric, reduce porosity and retaining heat. However, above the lower critical solution temperature, the hydrogel shrinks, porosity increases, and so does breathability. For textile applications such as SUBBIMATT, the critical requirement is that this transition occurs within a range of 25 to 32 degrees Celsius. Now, before presenting the experimental methodology and results, let me briefly introduce some basic rheological concepts that are relevant to hydrogels. Now, rheology is the study of how materials deform and flow under applied forces. So it's an internal, regarding viscosity, it's an internal resistance to flow or deformation, often described as a thickness or a stickiness. So in other words, it represents the friction between molecules in a liquid or gas medium with high viscosity fluids like honey, for example, flowing slowly, and low viscosity fluids like water flowing quickly. Now back to the hydrogel part. Hydrogels are viscoelastic materials, meaning they exhibit both solid-like and liquid-like behavior. Now this behavior is quantified using two key parameters: the storage moduli, we call it in brief G prime, that represents the elastic or solid-like response, and the loss modulus G double prime, which represents the viscous or liquid-like response. Now, when the storage modulus is higher than the loss modulus, the material behaves more like a solid, indicating the presence of a stable network. On the contrary, when the loss modulus dominates, the material behaves more like a liquid. Now, these parameters are particularly important for hydrogels as they allow us to understand their internal structure, monitor transitions such as gelation, and of course evaluate their mechanical stability under different conditions. Now, in our experiments, we use a plate-to-plate geometry, as we call it. Now, the hydrogel sample, is placed between two plates, two parallel plates, and the upper plate applies a small oscillatory motion. This creates a shear deformation in the material, and the instrument measures the resulting stress response. But of course, by controlling parameters such as strain, frequency, and temperature, we can probe the material in different conditions. From this response, we extract the storage and loss moduli, which describes the mechanical behavior of the hydrogel. So, as you may understand, rheology is critical at this point to assess our formulation, and in NTUA, the rheological measurements allowed us to determine the transition temperature, monitor gelation behavior, and evaluate the viscoelastic properties. So our experimental approach is based on oscillatory rheology. What we did first was to perform what we call strain sweep tests in order to define the linear viscoelastic region. Now, this is the range of low deformation, where a material's viscoelastic properties, for example, the storage modulus, are independent of the applied force, thus ensuring a linear relationship between stress and strain. So after that, we perform a temperature ramp test with tinkering the heating rate under, of course, low deformation to remain within the linear viscoelastic region. We monitor the storage modulus, G prime, which represents elastic behavior, and of course, the G double prime, hence the viscous behavior. Now, the transition identified through changes in this moduli as temperature increases. So let's go to the good part, our results starting from the fully bio-based systems. As you can see in this slide, at low temperatures, all systems comprising from either methylcellulose, hydroxypropyl methylcellulose, or hydrogen exhibit low storage modulus values, which indicates weakly structured networks. As temperature increases, a sharp rise in G prime can be observed in some cases, which corresponds to the thermally induced gel formation. However, the key observation here is that this transition occurs at relatively high temperature, typically between 50 to 70 degrees Celsius, depending on the composition of its hydrogen. Although blending with hydrogen slightly affects this transition behavior, it is not sufficient to shift the lower critical solution temperature into the desired temperature range of our application in SUBBIMATT project. Also, on the bottom of the slide, there are some viscosity data that also confirm the trend we referred to before, showing a corresponding increase into the transition point of the hydrogens. So overall, while fully bio-based systems are proven to be thermoresponsive, their transition temperature is too high for our application, highlighting that we need to experiment even further with our design strategy. So speaking of challenges, this is an interesting challenge that arises from the previous slide and the rheological measurement. So hydrogels comprised solely from bio-based materials have transition temperatures that are above 40 and 50 degrees Celsius. Even with tinkering the formulation with hydrogen, we could not reduce this transition temperature drastically. So to address this, we followed, let's say, a hybrid approach, and we kept the polysaccharides into our recipes. However, we added a synthetic ingredient, as Faye already mentioned. So we had a polysaccharide backbone consisting of cellulose derivatives and hydrogen, and combined it with isopropyl acrylamide. So the goal was to achieve precise control of the thermoresponsive behavior while maintaining as much as bio-based content as possible. And our compromise was at a very good analogy, 50% bio-based content and 50% synthetic one. So to overcome these limitations, as we said before, we experimented with these hybrid formulations, and we already mentioned that this was the top performing one and the most promising one in terms of temperature, the phase transition. So in contrast to the previous systems, now this one, with the code name of CP14, exhibits a clear transition in the range of approximately 25 to 30 degrees Celsius, which falls within the targeted temperature window of our application. Now, this transition is consistent across repeated measurements, as you can see on the right of the slide. And we also, for comparison, tested the pure synthetic polymer to be sure about the transition, and we can see that it's happening at a similar region, which confirms that it has a really critical role in our hybrid system. So the slight variation that someone can notice in the transition temperatures in the hybrid formulation can probably be attributed to factors such as the inhomogeneity of the sample or some thermal gradients during the measurement itself. So overall, this system successfully shifts the thermoresponsive behavior into our application range. So to sum things up, the observed transition is driven by changes in polymer-water interaction and As already noticed, as temperature increases, the network becomes less hydrophilic, leading to shrinkage and changes, of course, in the mechanical properties of the formulation. So in conclusion, fully bio-based systems show limitations when we aim to achieve our desired transition temperature, which is in fact close to the regular body temperature. However, hybrid systems allow precise tuning of our lower critical solution temperature and improved performance. And of course, last but not least, rheology plays a key role in understanding and validating the behavior of these thermoresponsive materials. So this was all from my side, and thank you all for listening to this presentation. And I will give the floor to Kate in order to conclude this webinar with her session.
Thank you very much, Konstantinos. I will start sharing also my screen, and you will have now a look on the wettability testing that we do inside the SUBBIMATT project. So why wettability matters in smart textiles? Wetting is a fast bridge between material design and textile function. It governs the first liquid surface interaction. So we are talking about spreading, pinning, or absorption. It is sensitive to coating chemistry on the roughness of the textile and the coating on porosity and on the hydration state. For smart textiles, a wetting change is often the first visible sign of a functional response. So we need to study the surface design, its chemistry, the roughness, as mentioned before, of the fabric itself or the coating, and the cross-linking of the material on the surface of the fabric. So how wetting is measured? It can be measured through static contact angle measurements, through the spreading, so this is a dynamic testing, on its absorption or possible hysteresis. With this, we could understand the textile function to quantify its comfort, its permeability, possible protection, and also some sensing in some cases. So we need to know a few things about the wettability basics and what actually the contact angle tells us. All the phenomena is guided by the Young equation. So actually we separate the materials to hydrophilic or hydrophobic. We could also have super hydrophilic or super hydrophobic cases. For a hydrophilic material, we have stronger solid and liquid affinity. And for a hydrophobic material, we have weaker solid-liquid interactions. The Young correlation, the Young equation actually combines the surface tension of the solid with the liquid, or the solid with the gas, or the liquid with the gas. So actually we are studying the triple point within three different phases of materials. And the connection point of all of them is the theta angle that can be measured through the contact angle measurements. A low theta means that the liquid spreads more easily across the surface. A high theta means that the spreading is limited and the surface appears less wettable. On fabric specifically, the measured angle is often an apparent value because fibers are rough and absorbent. So every time that we are making a measurement, we need to report the drop volume, the time after deposition, the liquid type, and which phase of the fabric was tested. For you to understand the theta, it's actually the tungsten on the triple point between the liquid, the solid surface, and the air. So how we do this type of measurements, especially on textiles? We have a flat surface where we place on it the textile. We try to keep it flat, and then we dispense a definite droplet. We need to calculate the volume of this droplet in order to be able to drop and not have a sessile drop on the surface of the fabric. Afterwards, we capture the droplet profile and try to fit the angle with a specific software on the machine that we have. Most of the times we have to fit both the left and right contact angle. On textiles, we face a practical challenge, which is the absorption and wicking that can reduce the angle during the measurement itself. So actually, we cannot have always static measurements, but most of the time dynamic ones, and to study the phenomenon on specific time intervals. Let me see. Yep, let's proceed in the next. So what controls the measured angle? First of all, the surface chemistry. Polar groups raise affinity to water, while non-polar ones reduce it. Then it's the roughness and porosity of the fabric. The fabric texture amplifies apparent wetting and can accelerate imbibition. The coating also continuity is very important. So if we have a patchy coverage, this can give a mixed wetting. Also, the stronger cross-linking can stabilize the finishing. Last but not least, we have the temperature and hydration, especially for smart textiles that would like to function with an openness for functionality. So here we have responsive polymers that can shift swelling. We need also to study the mobility of the chains and the surface energy based on the heat. A smart hydrogel coating matters because it can change at least one of these drivers when the temperature changes. So this means that we also need to measure the wettability because we understand how this smart textile can function. So here you may see at real testing when trying to make contact angle measurements. In both cases, we have applied an NTR hydrogel that can be synthesized in the lab. On the fabric, it's the same fabric piece in both cases. In the first case, however, we have not cross-linked the material, the hydrogel. While in the second case, there is a cross-linking between the hydrogel and the fabric. So you may see that we have differences on the wettability. And also, we do not study only this type of phenomenon, but we are trying to determine also differences between the reference fabrics. So what is the procedure of the wettability testing? We start with the dosing, which means that we are using a syringe to deposit a controlled volume, typically from 1 to 20 microliters of the testing liquid. Most of the cases, this is water. If we want also to study other phenomena, we can use some specific solvents, especially when we want to determine the surface free energy. So we are spreading or rinsing or dropping the drop with a specific syringe or a specific volume on the surface that we want to study. Then we need to capture the profile of this drop on specific time intervals. Most of the cases we have the time that the droplet is attached on the surface. So this is the 0 point. In other cases, we could also have extra time intervals when we need to study a dynamic phenomenon. Then there is the image acquisition, where we use the camera and light source to take the picture of the droplet's profile, and the analysis. The analysis is made through a software of the equipment that we're using, and mainly we define the baseline, so which is the surface, and try to fit a curve with specific calculations and simulations. Most of the time, we are using a Young Laplace equation, or it could be also an ellipse in case that we don't have really round droplets. So the point here is to determine the angle, the theta angle. In a dynamic measurement, we need to measure the advancing or receding angles and add or remove the liquid from drop while recording. That's why in these cases we're taking a video and then try to make calculations during the whole procedure. So what we could see also in our case in SUBBIMATT. In the first case, when we have a fabric sample that's not treated, you see that we can have a drop at 0 point, and after a while, the water is totally absorbed, so we cannot observe the drop anymore. When we have coated the fabric with the NTR hydrogel, we can see that we have like a waterproofing function. So in the beginning, the droplet it has been absorbed, but as the time passes, it still remains on the surface. So the change in the contact angle that can be recorded also in the diagram shows us the hydrophilic or hydrophobic character versus also time. So it's a dynamic measurement. By this, we are able to see if our coating with the hydrogel was effective, not only in terms of their functionality, but also waterproofing if this functionality is also needed. So we would like to close this presentation with some applications for smart textile with NTR hydrogels to understand a little bit why and where we can use this type of materials. And this is, for example, in adaptive moisture or heat management. Thermally triggered wetting can help textiles regulate liquid spread and comfort. On the controlled permeability or filtration, where responsive coatings can tune passage of water or other fluids with temperature. On biomedical dressings and transdermal systems, where hydrogel-coated textiles can support moisture interfaces and on-demand release concept. And on wearables, sensing and actuation, where temperature-sensitive layers can combine with conductive or structured textile functions. And in this case, these materials can be combined also with carbon-based nanomaterials. So the take-home message of today's webinar is that contact angle is a simple but powerful surface readout. It gives fast a way to see whether a smart coating changes and how the textiles mix water. Negative thermoresponsive hydrogels convert temperature into functional surface changes. For LCST-type systems, a higher temperature can collapse the network and shift the apparent wettability. And it's a meaningful validation that it's both hydrogel tests and textile-specific durability tests to understand how a smart response works, and only matters when it survives real use, which is the moisture, bending, washing, and to withstand several cycles of use. By this, I would like also to thank my team, Professor Kostas Haristidis, who is the director of the lab, and my colleagues Konstantinos, Faye, and Georgina. We are working all together at SUBBIMATT project. And thank you very much for your attention.
Thank you very much, Kate. Thank you very much, Kostas and Faye. And thank you all for joining. I think we have quite a few minutes for if any of you has any question for our speakers. So I would wait another couple of minutes to see whether questions will come on the chat. Meanwhile, I would like to say that it was a very interesting presentation from all of you. I would also like to remind that we have quite a few channels in which you can follow everything that is going on within the SUBBIMATT project, which is very interesting. It hasn't started a long time ago, so results are still to come. But we have interesting articles on our website, so you can look up to them. We also have one scientific publication, indeed, from the University of Athens, which is on our publications page. We have a news and events section on our website, which I will share the link in the chat, so you can check the participation to events of our partners and also the articles that I was mentioning. Other than these, we also have other channels. We are present on LinkedIn, where we share interesting insights on the SUBBIMATT projects and all of its features, and also we have a YouTube channel where we share the project video, which is already published, and we will publish another video. Probably we will come up with the interviews and other interesting topics. Meanwhile, I see that there's a question from Amaya. So I don't know to whom the question is referred to. Kate, maybe you want to take a look at the question. Do you see it in the chat?
Now I'm reading the question. It's from Amaya.
Okay.
So she's asking that she would like to know if the increase of the porosity of hydrogels with the temperature is reversible and how many cycles this effect will last. I was thinking for sure Faye can answer this, but just to mention that the porosity it's difficult to be determined, especially when we're talking about a hydrogel that it's in a liquid form. So Faye, if you'd like to give an answer to Amaya.
So the entire hydrogel, like the gel by itself, it is reversible. We haven't tested the cycles yet, but I've been working with our composition for at least, I'm doing tests for at least 5 months now. And every batch I've tried, it is still reversible after even my first one that I kept is still reversible even after 5 months and multiple cycles because we do reference testing for the water bath and the rheometer. So I haven't tested how long or how many cycles will it take for the hydrogel itself to stop working. This is the one thing. And the second is that it's mostly about how the hydrogel is grafted onto the fabric, how well the hydrogel is grafted onto the fabric. And in order to have the hydrogel continue working rather than the functionality of the hydrogel itself, like the stability and the cycles and the pore size. So we haven't tested, we have tested how much of the hydrogel is maintained after like 2 washes, but not after 3 cycles. We haven't done those breathability testings on washed fabrics. I think, okay, perfect.
Thank you, Faye, for the answer. Thank you, Kate. No more questions, I see. Okay, I have left a few links regarding the SUBBIMATT project communication channels that we have. So if you are interested in any of these, or if you want to get in contact, there's also an email, a dedicated email in the contacts page. So visit and get in contact if you are interested and want to know more. No questions from the students. I guess it was very clear.
So either we were very descriptive or nobody understood anything.
I think it was pretty clear, so I think it was very well done. Very nice presentations, very clear, very interesting, and a lot of insights. I think we can close the meeting. Very good presentations, yes. Thank you for the comment. It's very helpful to have feedbacks from the audience. Thank you. So I think we can close the meeting. Thank you everyone for joining. As I said, it is recorded, so it will be online on our channels. Thank you to all the speakers for the presentation, very interesting, and for the responding to the questions. Okay, so we will have another webinar probably in 3 to 4 months, which will be the third one, and you will also receive an invitation when we will know the topic, the date, and the time. So thank you for joining, and have a nice evening. Thank you.
Thank you very much, Andrea, for the organization. So we are open to questions also during our lectures. So have a nice afternoon.
You too. Ciao, ciao.
Yeah, goodbye, everyone.
Bye.
Bye-bye.